One is the wedge. A wedge is basically any blade is a wedge. And you can think of a wedge as a double-sided inclined plane. And a wedge like this changes the direction of force and also multiplies force. A wedge can transfer a downward force into an outward force, which can split or cut an object. If you look at this first diagram here, what you see is a downward force, which is this arrow, on the wedge, is transferred to an outward force, pushing to each side. And that's what cuts an object. Has anyone ever used one of these wedges as a log splitter? You ever had to like cut firewood or split firewood?
Yeah.
Basically what you do is you have this metal. It's just a wedge, just a triangular sort of piece of metal. You put it on a log, okay, and then you hit it with a sledgehammer or something. And what happens to the wood? It splits apart. You're taking this large downward force that you hit the wedge with, and it's pushing outward, which is what causes the log to split. Any blade, a knife, is the same thing. You're exerting a downward force on the knife, and that blade is exerting an outward force that splits whatever object you're cutting along that plane. So a knife, scissors, the tip of a nail, these are all wedges. And the thinner and longer the blade is, the greater mechanical advantage it gives. Should make sense. If you think about it, if you have this wedge here, you're not going to cut yourself with it. Big wedge. It doesn't have a very high mechanical advantage, but a thin, very sharp blade does. All right. Another type, so again, this is just two inclined planes back to back. A screw is also really a type of inclined plane. And if you imagine a screw, you could think of it as an inclined plane wrapped around a cylinder. And that's what form. What do you call the ridges on a screw? Threads, the threads of the screw. Screws are used for fastening objects together, but lots of other things as well. Holding things tightly together, sealing things. If you think about, if you use a screw to attach two pieces of wood together versus a nail, what's the difference in the force you have to apply? To attach the piece of wood with a nail, what do you have to do? Hit it very hard, okay, with a hammer, exerting a great force on that screw. On that nail. How about a screw? Just have to turn it. Do you have to exert a great force? Not as much as hitting that nail with a hammer. You can exert, but the trade-off, it takes a lot of distance to do it. Okay? And actually, screws come, if you go to the hardware store or something to buy a screw, one of the things you can buy is screws with different threads on them. Different numbers of threads, and then pass these around, and different steepness of those threads. And those two types of screws have different mechanical advantages. Okay? And we'll talk about that in a second. This is also, you know what this is? Have you seen one of these?
It's a diamond.
You may have seen it if your parents got a flat tire and had to change it.
Oh,
to jack. Yeah, this is a jack, and right now it's extended, but it starts off flat and small, and you put it under the car. This end is basically a long threaded rod, a screw, and you attach a little handle to this end, and as you turn this screw, it lifts the car up. You don't have to turn very hard, but if you've ever seen somebody use it, how many times they have to turn it to lift the car? A lot of times, because those threads are very thin, and so it takes a long time to lift that car using this jack, but obviously it greatly multiplies your force. Normally one individual can't lift a car, but by using this simple machine, you can. Tom?
I've seen someone use that one before, but the one that Dad used was like,
yeah, there's also a different hydraulic jack and pneumatic jack. So on the screw, the steeper the threads, okay, the less the mechanical advantage. So as I pass around those screws, where are they? Do you notice the difference in the threads? Yeah. One has lots of threads wrapped around it that are not steep at all. The other has fewer threads and they're much steeper. Okay. If we look at them, we could think about them as this type of screw and this type of screw. Now screw A, threads are not very steep, there's a lot of them. If you're using this to screw it into a piece of wood, how do you think it would feel to use this screw versus this screw?
easier.
Which one would be easier? Brandon? B would be easier?
They're not. They're.
You mean less force?
Yeah.
Okay.
It'd be the same.
Same?
They're not the same.
It would be easier because A has more different.
A has more threads.
But B has.
If you were to unravel the screw, if you were to unravel the threads, which would be a longer inclined plane? A. That one has the greater mechanical advantage. If you think about it, as you turn that screw, each revolution of the screw, how far into the wood is it going to go? Just a tiny bit each time, right? So how many times do you have to turn it to get it in all the way? A lot. Well, what do you think about the force? You're going to have to not use much force. It's not going to be hard to turn, but you're going to have to turn it a lot of times. Screw B has steeper threads. You're going to have to exert a lot more force, but how many times do you have to turn it? Fewer times. We have that trade-off. Distance for force. So if we look here, if you were to put a piece of string around the threads of the screw, you can actually do this. Wrap a string around all the threads, unravel it. You can basically see how long that inclined plane is. The longer it is, the more mechanical advantage. So in this case, let's say the thread length was 16 centimeters. The length of the screw was 2 centimeters, giving that screw mechanical advantage of what?
4.
8. If I did it for the other screw, which has a shorter inclined plane, the mechanical advantage would be 4. But this one would take twice as many turns to get into the wood versus screw B. So that's the trade-off. All right, another type of simple machine is a wheel and axle. A wheel and axle is basically a larger wheel, usually, that's attached to a rod called an axle. So as you move the wheel, the axle also turns. And often a wheel and axle is used to multiply your force. Has anyone ever had in your house an older, if you have an older house, an older doorknobs? Has anyone ever had a doorknob like this and the handle comes off?
Yes.
All right. And then just that threaded rod is poking through? Did you ever try and open the door by turning that rod?
Yes.
You could grab it and turn it. Is it hard? Yeah, it's pretty hard to turn that rod. Adding that knob is creating a simple machine, a wheel and axle. The bigger the knob, the easier it would be to turn that axle. But again, if you have a huge knob this big, what about distance? Got to do it a longer distance to use that machine. In this case, for example, if we had a doorknob that had a radius of 12 centimeters attached to a rod that had a radius of just 2 centimeters, the mechanical advantage would be 6. You know, any door, even this, doesn't look like a doorknob, this handle, but it is. You could think about this, if it were a knob, it would be a huge knob this big around. But you just have the handle part. So again, this gives you a great mechanical. I don't have to push with much force here to move the bolt in and out. How does that doorknob compare? Smaller, therefore what? It's harder to use. I have to exert more force to use this one because it has a smaller wheel part. There's lots of examples of a wheel and axle on your bike. If you're going up a hill, which gear do you put it on? The lowest gear, which is the smallest wheel on the front gears of your bike. And so you can get up a steep hill on that low gear. You don't have to exert a lot of force, but what's the trade-off? You got to pedal those, right? You got to make lots of rotations of those pedals to move your bike very far. You're using less force, but greater distance. If you put it on the highest gear, think about what that's like. That actually works in reverse. You have to put a lot of force in, but one rotation of the pedals, and how far do you go? Go really far, but you have to use more force. You have that constant trade-off with simple machines. Has anyone ever seen one of these boat lifts?
Yeah. No. Oh yeah, I have one.
Like if you go to somebody's camp or something, if they have a boat or jet ski, you drive the boat up onto it's in the water, then you get out and you start turning this huge wheel. Okay? And that slowly lifts the boat out of the water. Has anyone ever used one of those? Okay. So how many times though do you have to turn the wheel to get it out of the water? A lot. But because it's that huge wheel, it multiplies your force a great deal. You can lift the whole boat out of the water with one hand just going like this. But you need to do it for a greater distance. Okay. Other examples here are doorknobs and things like that. Those are all wheel and axle. Also a socket set. You know what a socket set is?
It's a light bulb.
Put the socket and it's got a handle on it.
Oh no, never mind.
And then you turn it. Okay.
Oh yeah.
Yeah, and so that turns it. So the longer the handle, the greater mechanical advantage it gives you. The easier it is to actually remove a bolt. Skipping, sorry. All right, a pulley. Pulley is a class of simple machines. And there are several types of pulleys. And pulleys basically a grooved wheel, such as this, that you wrap a rope or a string or a chain around, and it gives you mechanical advantage sometimes. The way that you calculate the ideal mechanical advantage of a pulley is by looking at how many parts of the rope are supporting the weight that you're trying to lift. This is called a fixed pulley. It's like this. Basically a pulley. Okay? It doesn't move, stays here, and I attach it to a weight and I pull on the object. That's a fixed pulley. How many parts of the string are supporting the weight?
One.
Just this one. That gives it a mechanical advantage of just one. So this one doesn't actually allow me to use less force. So why would I use this? I can't. It's not allowing me to use less force. I have to use the same amount. Brandon?
So you don't have to lift it up. You can just like pull the rope.
Yeah, you can pull in a downward direction, and that lifts the object up. So again, it changes the direction of force. That's one of the uses of a simple machine.
How come it's spinning?
I was just wrapped around there. So this gives you a mechanical advantage of one. Now, can also calculate the actual mechanical advantage if I measure the mass of this object and I measure the force to pull on it. That would give me the actual mechanical advantage. In this case, if this mass were 100 newtons and I pulled with 100 newtons, give me actual mechanical advantage of what? 1. Does anybody see a problem, an error here? Would it really be 1 in real life? No, if this object weighed 100 newtons, would I have to pull with 100 newtons of force? What would I have to pull with? More or less? Less? Why? More? Why? You're saying words. Nicholas?
More because of friction.
More, because there is some friction here. So I have to both overcome the friction and lift the weight. Maybe I'd have to pull with 101 newtons. But this problem, the way I described it, it doesn't. I'll take that into account. So that's a fixed pulley. It changes the direction of the force, but not necessarily the amount. Another type of pulley would be a movable pulley. Let's see if I can do this. In a movable pulley, the pulley actually moves. Let's see. I don't know if this is going to work. All right, so now, still the string attached. No, it's not going to work. So what you see is how many parts of the rope are supporting the weight in this? 2, giving a mechanical advantage of 2. Get the idea. So again, if I pull up, because 2 parts of the rope are supporting the weight, I only have to use half as much force. Okay, that's a movable pulley. Pulley moves.
Wait, why are there 2 parts? Which 2 parts?
See, this string and this string are both supporting the weight.
Aren't they the same thing?
It's the same string, but parts of the string. Yeah. Okay. Then there's the combination pulley. This is made of a fixed pulley on top and a movable pulley underneath. So I could set this up, should I? Probably not. It's going to be hard. All right, so if I have a pulley on top, I thread this string through the second pulley. And then go back up. All right, so now, is this working? I'm not going to be able to do it. It's going to take too long. I'll set it up after if not. But anyway, you have a pulley like this where you have the string wrapped around several times. In this case, how many parts of the rope are supporting the weight?
4.
1, 2, 3, 4 parts are supporting the weight. Therefore, I'm only going to have to use a quarter of the force. Gives me a mechanical advantage of 4. Okay. You could say, if you have a string wrapped around many, many times, you can have a mechanical advantage of 8 or 10, making it very easy to lift a weight. It like a garage, like an auto garage. Sometimes they'll have this big system of chains set up to lift the engine out of a car. And they can have that, they can lift the engine out with just a single hand because of this pulley system, but they have to move the chain a lot to lift the engine out. Cranes use pulleys like this, these movable pulleys. All right, our last simple machine is the lever or lever.
No one calls it a lever.
Some people do.
It's not clever.
So a lever
No.
such as this is basically a rigid board or rod that pivots around what we call the fulcrum. And it can be used to multiply force. that's being applied to an object. And when we talk about levers, we break them into different categories. We call them classes of levers. They're called first class, second class, and third class levers. And they're named, you can think about it as based on what's in the middle. Is it the fulcrum, the resistance, or the effort? So if you think about this lever here, what would this be? Fulcrum, resistance, or effort? Here. That's a fulcrum. What's this? Resistance. Where are they putting in the effort? Here. So that's the effort's in the middle. What class lever would that be? Third. If you remember the word free, that'll help you to remember which class is which. Because if it's the effort in the middle, it's a third class lever. I don't know. Because FRE doesn't make a word for you to remember.
Ref?
But then it wouldn't be in the correct order.
Ref not?
No, it wouldn't be in the correct order. So this would be a third class lever. What about this one? What's in the middle? What class? Second class lever. Because the resistance is in the middle. And this one, what's in the middle? Fulcrum. First class lever. First class levers are useful. I have this set up right here as a first class lever. I have my resistance way down there. I have my fulcrum here in the middle. And I can put the effort in here. Okay, so I'm lifting that object. I don't have to use much force to lift that object. Okay? Multiplying my force. But how about look at the distance? How high is that object going to travel? I don't know, this high maybe. But how much distance do I have to cover? A greater distance. So that's the trade-off. Okay? When you're calculating mechanical advantage for a first class lever, okay, we have effort distance is the distance from the fulcrum to the effort. In this example, it's 150 centimeters. Resistance distance is the distance between the fulcrum and the resistance. In this case, it's 50 centimeters. So the closer the fulcrum is to the resistance, the greater the mechanical advantage. If I wanted to increase mechanical advantage, that would be, I just move that fulcrum closer to the resistance, and now I barely have to touch it to lift that weight. You just sort of tap on it and lift the weight. Tiny force can lift that object up. So this one would give me this example, a mechanical advantage of 3. For a lever, I could also calculate the actual mechanical advantage by using the forces. I know the force required to lift that weight, I can measure it, and I can calculate the force I need to pull on this. And by dividing them, I would get the actual mechanical advantage, which of course would always be would be somewhat less than the ideal. Teeter-totter is an example of a first class lever. If you have two people on a teeter-totter of unequal size, what do? How do you account for that?
Move the fulcrum more to the heavier side.
Yeah, you can move the fulcrum closer to the larger person. Some teeter-totters actually can take it off and move it. You ever seen those ones?
Yeah.
You could like lift the board up and it's got a little bracket under there. What else could you do? Brandon?
You could have the heavier person sit closer to the middle.
Yeah, you can have the heavier person sit closer to the fulcrum. And again, you could do that until there's the balancing point. Okay. Can opener is a first class lever. A crowbar is a first class lever. Okay, they can multiply your force. Second class lever has a resistance in the middle. And again, I could set up my lever here. Okay. So now I have my fulcrum at one end. Here's my resistance. And now I can exert my effort here to lift this object by lifting up on this. Again, I don't have to use a lot of force. But when I move this lever this great distance, how much does the weight move? Not very much. Okay, so there's the trade-off. The closer the resistance is to the fulcrum, greater the mechanical advantage. A nutcracker is an example of a second-class lever. You have the fulcrum up here at the pivot. The resistance is this walnut. Effort is where you squeeze the handle together. Again, in this case, what would the ideal mechanical advantage be for this example lever up here? What would it be? 3. The effort distance is 120 centimeters. The resistance distance is 40, giving me mechanical advantage of 3. When I do it using the forces, the actual mechanical advantage would be a little bit less. It's about 2.3. And that brings us to our last lever, third class lever. A wheelbarrow is another good example. Second class lever. Where's the fulcrum in a wheelbarrow? The wheel. What's this? Resistance. And your effort is here. Okay, so you can lift a heavy weight with using less force. Third class lever. Third class lever is the effort in the middle, which is a little different. It actually doesn't increase your force. If I put my weight here, now I could lift in the middle, I could exert my effort, but it's harder to lift. I actually have to use more force to lift it this way. So I have to use more force, but what's the trade-off?
Less distance.
Yeah, I only have to move my hand a tiny bit. Look how high the weight is going. So I'm using more force, but I have to do it for less distance.
So is that supposed to say increase your distance but not force then?
Well, it depends. It's not, so it increases the distance that the object moves.
Okay.
Decreases the distance I have to move my hand. You know, so examples of third class lever. Okay. Depends on how you use the hockey stick. See these lax bros here? You could, if you think about, if you hold your lacrosse stick at the bottom, you hold your hand sort of as the fulcrum. What's the resistance? The distance is up here, the ball. And where do you put the effort in? The middle. So by making a small amount of movement with your middle hand, okay, the head of your lacrosse stick moves a greater distance. You can move at a greater speed, letting you throw that ball. Your bicep works as a third class lever. Okay? Your hand is the resistance. The fulcrum is your elbow. The effort is where the muscle attaches to the forearm bones. What were those forearm bones called?
Ulnar radius.
Ulnar radius. So, in this case, you only move the lever a small amount, but the resistance moves a great distance.